So now you've learned all about polar coordinates and how to graph stuff. We need to actually do the calculus since we are in calculus. In this video, we're going to talk about how to find the area of those various things we graphed the other day, and also maybe the circumference or arc length of these graphs as well. So first, let's talk about how we're going to apply the calculus. The area of a sector, we have, let's say the theta is how much of the sector we want to find the area of, just normal circle. Well, the area of a circle is pi r squared, and the percentage or the fraction of the circle we have is theta over 2 pi. So if we simplify, we get r squared theta over 2. So if I want the area of this section of a circle or sector, it's r squared theta over 2. Now, how does this help us with the calculus? Well, just like when we did the areas with our functions going above the x-axis or below, and we chopped it up into a bunch of rectangles, we don't do rectangles this time, we do little sectors. So suppose we have this function, r is f of theta, and we want to sweep between theta equals alpha and theta equals beta. I want to find this area. Well, just like before we chop things up, we're going to chop this thing up, except this time we chop it up into sectors. And I can either use the left side or the right side, just like we did with the rectangles, estimate the area. And also, the more sectors we have, the better our estimate. The area of one single itty bitty sector is going to be the radius squared, which in this case is f of theta, over 2. And our delta theta represents how much of those little thetas we are chopping it up into. And as before, we're going to take the limit as n goes to infinity. This delta theta becomes a d theta. So the equation for a polar area is the integral from alpha to beta of f of theta squared over 2 d theta. So let's see if we can find a couple areas. The first one, it appears theta is going from 0 all the way around to 2 pi. So we're going to integrate. My formula, we have integral from alpha to beta of f of theta squared over 2 d theta. So in this situation, I have the integral from 0 to 2 pi. My function is the square root of theta, which I will square and put over 2 d theta. We'll bring the 1/2 out front, integrating from 0 to 2 pi. The square root of theta squared is just theta. Do my calculus magic, I get theta squared over 2. I'm taking this from 0 to 2 pi. I have 1/4 times, if I put 2 pi in here, I get 4 pi squared minus 0. 4's cancel, so the area of that region is pi squared. So not too bad. Well, the integral is not too bad. And it wasn't too hard visualizing this one. Sometimes it gets a little funky, this one. Now here is the cardioid. We've got r equals 1 plus cosine theta. To go from 0 to pi, we get the top half, and then we keep going to get the bottom half. So we can either do only half of it and say times 2 or go through the whole thing. So the area will equal the integral from 0 to 2 pi of my function, which was 1 plus cosine theta. I'm going to square it and put it over 2 d theta. Okay, so let's crank this out. I'm going to pull the 1/2 out front because it's a pain in my butt. Multiplying that out, I get 1 plus 2 cosine theta plus cosine squared of theta, d theta. That's going to be a little bit of work, but this is straightforward. Let's just go ahead and do the whole thing at once. So I'm not going to integrate yet. Rewriting this as 1/2 1 plus cosine of 2 theta, d theta. Simplifying. I have a 1, I've got a plus 1/2, so I have a 3/2 plus 2 cosine theta plus 1/2 cosine of 2 theta d theta. Now I can integrate, and I have 1/2 times 3 over 2 theta plus integral of cosine of sine. So I have 2 sine of theta. Cosine of 2 theta, I integrate that. I have to divide by the 2. So I have 1/4 sine of 2 theta. And I'm taking that from 0 to 2 pi. Now, sine of 2 pi or 4 pi or any integer multiple of pi is just going to be 0. So these things are going to go away when I put in 2 pi and when I put in 0. The only thing that's going to survive is 3/2 2 pi and then minus 0. So I have 2. I have 3 pi over 2 is my area. That's not too bad. This one's tricky. Okay, so we've got 1 plus 2 cosine theta, but we've got this little chunk in here. So I could think about, this is when the whole expression is negative. And this is going to be negative when 1 plus 2 cosine theta equals 0. So it's going to start being negative when theta is, what, 2 pi over 3. Don't worry about that yet. So I would integrate this and then subtract, but that would include all that white spot here. But then I would subtract this part and then add this part. Now, the cool thing about this, though, is if I were to integrate straight from 0 to 2 pi, this is already going to be negative because the reason it's popping back over into the section is that my radiuses are negative. So when I integrate this, I will automatically get the negative value here. So all I have to do is integrate from 0 to 2 pi of the entire expression. So we know how to integrate this. I'm just going to cut the chase. The integral of this becomes pi. So that's how you would integrate these polar graphs. We're not going to do any really weird, crazy ones, but maybe a few somewhat fun ones. You know, we're going to do the ones with leaves because I like things with leaves. And I think that's a good place to stop.